log into the Pi. Okay, so we kind of stopped in the middle. We didn't quite finish last time, so let's go back there for the moment. That is not the file I was looking for. Okay, I must have not copied it over. Yeah, okay, hang on. I didn't copy it over from my USB key. So, Jack, how you doing this morning? Or evening, I guess, for you, but okay, so this was the file we were looking at. Okay, so just to kind of recap the difference here, we learned that there's really three types of move instructions, and we discovered sort of by accident one of the kinds. Okay, so then we were talking about the flags. So just to remind ourselves, the flags that we'll be dealing with are NZ, C, and V. So negatives, 0, carry, or overflow. And these things will be the basis for conditional instructions. So what would happen is you would do some sort of either computation or comparison, and then that would set a flag or flags to something, and then you would say, okay, I'm going to make the decision as to whether or not to do a jump based on what the status of the flags are. Some of those only look at one flag, some of them look at multiple flags. Okay. Now, this is not something we had in Brookshire, because in Brookshire, what was the only sort of comparison that could take place? Well, it's the jump command, but what were the details, right? How did it do comparison? Yeah, register something got compared to register 0, and they were either the same or they weren't, right? So in a sense, the Brookshire architecture had a single flag. Maybe we could call it E for equality, or possibly Z for 0. But it was not an accessible thing, right? It just happened. Um, that would be something that if we designed sort of a Brookshire 2.0 architecture that I'd personally want to throw in. Okay, so those were our flags, and we talked about the difference between flag setting and flag reading, and flag setting and reading instructions versus ones that don't care about the flags, right? So for most operations that are of an arithmetical or logical nature, you tack an S onto the instruction mnemonic, and it will set flags when the computation is complete as appropriate. And then there's some of them, like add with carry, that will read what the carry flag is, and then sort of throw that into the computation. Right. Okay, so we've got all of those things. Okay, so then we wanted to start talking about jumps, right? So on Brookshire, right, we only had jump or a branch on equality. The only way to jump was to compare a register to register 0. And there were sort of two ways that we could use that in Brookshire: a conditional jump and an unconditional jump. And the unconditional jump, the trick was just compare register 0 to itself, right? Because no matter what's there, it's equal to itself. What are we missing this morning? 5, 6, 7, 8, 9, 10. Ooh, man, this is not good. No. Oh. Oh, and it looks like Dr. Dunaway's with us this morning. Good morning. He's rating our channel. Be sure to like and subscribe. Visit my Etsy store for sweet Dr. McKinney merchandise. No. Okay. So, right. So ARM, fortunately for us, has way more variations on branching. Okay. So we have uh, unconditional branching. Okay, so this would be like what we did in Brookshire, where we deliberately compared register 0 to itself to force a jump to someplace. Okay, labels, right, were things that in assembly are just going to be like a textual label, but eventually are going to get resolved to be a memory address, just like on Brookshire. It's just that for us, the assembler and the operating system take care of all of those details. Okay. You can branch to the address that's contained in a register. You have to know what the memory address is in advance to do that, or be able to compute it somehow. And that, of course, would also be unconditional, meaning that it doesn't matter what's in register XR. You're going to set the program counter to its value, and then, hopefully there's valid instructions at that address. If not, then the program will crash. Okay, and so the real interesting stuff, right, will be the branch with a condition. Okay, and the dot cond here will have is going to stand for one of 16 different options that you could use. Okay, so it's the condition. Um, we'll talk about all those varieties in a moment. Okay, and those are going to be conditional on value or values of the NZCV flags. Okay, so some of the conditions look at more than one flag, others only look at one flag. It just depends. Okay, um, but in order to do the comparison, um, well, okay, so a couple of the choices that we're going to have are equal, not equal, greater than or equal to, right? Okay, so a lot of these are very arithmetic in nature. There are there is one of them that's branch always. There's another one, and you might think, why on earth would you ever want to use this? There is a branch never instruction. Okay, and why might you want a branch never instruction? A command that never actually does anything. Well, okay, yeah, maybe you're just feeling lazy and you want to make the Raspberry Pi feel lazy. But no, seriously, why would having such a seemingly silly instruction be actually a good thing in an instruction set architecture? And I've got a story to illustrate it. Hmm? Story time? Okay. So how many of you guys know Rob Shook? Rob Shook, class of 83, I think. Yeah, the man, the myth, the legend, right? Um, Works for IBM, uh, and lives in Austin, the Austin area in Texas. Um, yeah, like I said, class of 83. He was a psych major, and essentially a computer science minor, although we called it something different back then. Okay, great. Um, after after Wabash, he did a master's degree at I think Ohio State or maybe the University of Ohio, someplace in Ohio. And one of the things that he was doing, he was working with a professor in a like psychology research lab, and this was like I said in the mid '80s. They they were working on like they had some sort of animal or like nerve tissue from an animal, and they were connecting it to a computer to record nerve impulses. Okay, and they were using a 608020 processor, which is a Motorola processor of that era, and the timing was very important on this, so that they could record the stuff in particular ways. Okay, but it wasn't just a single loop that was running to record things. There were branches and conditions and all sorts of stuff like that, right? So different subroutines that he had in his program. And because of that, because of the timing, what he had to do was he had to make sure that each subroutine took exactly the same number of machine cycles to execute. And so if you had one routine that was much shorter than the rest of them, how could you make it take exactly the same amount of time as the rest of them? You put in a bunch of instructions that don't actually do anything, but take time to not do anything. Okay, so so what that meant was putting in uh, some architectures, and the 608020 did have this, have an instruction that's called no op, like don't do anything. Okay, um, and or branch nevers. Okay, now you might say, why use both of those? Well, depending on the architecture, maybe no op only takes one cycle, but branch never takes two, and so you could, right, kind of get the exact number of cycles that you need by combining stupid looking instructions in smart ways. Um, I wish he could. Well, I wish he was here talking with us, or we could get him on the owl camera thingy. Um, or he had some source code because it'd be kind of interesting to look at it. But he was doing this in 608020 assembly. Um, the 608020, by the way, well, just since we're going down that tangent for the moment, um, this is probably going to give me a zip code. Nope, actually, no. Good. Yay. Okay, so this was the 608020. 32-bit microprocessor released in 1984, so this would have been right after, right, he graduated from Wabash. And it could do 32-bit stuff. And so it was a slight enhancement of the 68K. The 68K was, or a variant of it, was used in the, I believe the Sega Genesis was, or Sega Mega Drive, which is what it was called in Japan. So, you know, other processor of this era. Yeah, so the 608020, that's what he was programming on, and it's amazing speeds of 33 megahertz. Yeah. Okay. Anyway, so that might be a reason to use things like branch evers and no ops, because I mean I can't think of why we would need that in perhaps our um, well, no, actually, I can't think of one possible example. So, um, for example, let's say so the Raspberry Pis have GPIO pins, okay, general purpose input output. So, how many of you guys have ever, well, those of you who are in 101 saw me do some demos with transistors using an Arduino, and I was connecting things to pins on the Arduino to turn stuff off and on, lights and whatnot. And maybe you've seen videos of this sort of thing. No? Okay. I don't remember what I did in I've been, tweaking and enhancing 101 for every time I teach it. I add something new to it. Anyway, um, if we were trying to do something where timing was important, right? Like let's say we wanted to turn a light on and off in some sort of predictable cycle. Well, depending on what kind of code is going on at the time, like let's say it was also doing a bunch of other stuff, we might have to be really cognizant of, okay, we need the light to turn on and off at specific times, and the amount of code execution between those should be identical so that the pattern doesn't get messed up. Um, and it is actually possible, and we'll talk about this hopefully later on in maybe a month from now, roughly, um, to control those GPIO pins in assembly. So we could like hook up a breadboard and a little LED and make it blink by programming it in assembly, and that's freaking awesome. Je pense. Okay, good. So that's why you might use a silly and seemingly silly instruction. Okay, so now typically right before you do a branch on a condition, you need to set the flags to be whatever they need to be to evaluate that condition, okay? And the arithmetic instructions will set flags, but they're not the only ones that can do it. Oftentimes we want to do a comparison, okay? So for example, let's say that you're writing a loop, right, of some sort, like say a for loop, right? What's the comparison that you need to make? You've got your counting variable, whatever it is, let's say I, and then you've got your max value that it tells you when the loop is supposed to finish. Okay, so like let's say you had for int I equals 0, I less than 5, I plus plus stuff. Okay, then what would you do at each iteration of the loop? You'd say, okay, I need to take the register that has my counting variable in it. I need to take the number 5 or 4, whatever, and I need to compare them, okay? And in the case of a for loop, you probably want to branch on um, less than, or maybe less than or equal, or perhaps greater than or equal, just, depending on which way you've arranged your loop, right? So like, when would we want to stop looping if we were doing a for loop 4 times? We'd want to stop when the counting variable hit 4, say. Okay, so we could set it up in a couple different ways. We could say, okay, when that thing is equal to 4, terminate the loop and move on to something else. Or when that thing is equal to 4, or say less than 4, go into this routine where you do stuff, right? So it just depends on how we want to structure it. But in any of those cases, we're going to be doing some sort of comparison between two numbers, right? So in the case of the for loop example, one of those numbers is your counting variable, right? The thing that gets incremented every time. And the other is whatever number you've chosen in advance to be the limit of that counting variable, right? And you need to compare them, right? And they're either equal or they're not, or they're less than, or whatever, right? And so what a comparison operation is going to do is it's actually going to subtract one of them from the other, okay? But here's what's sort of interesting. It really, so when you type compare x0, x1, what is it going to do? What it really does is it does this subtraction operation, okay? And just so that we're clear, what's the S at the end of subs? Tell me. It's going to set the flags, okay, to whatever they need to be. So what if I'm using the subtraction operation, like the addition operation, I need to specify 3 registers, okay? What's the first one? And I should actually have some commas here, right? So what's the first register that's listed? In this case, it's XZR, the 0 register. Okay, that's what's in the first position. Okay, but what is the first position always for this type of operation? It's the destination. Okay, so if you want to compute something, but you don't actually care about the result, or you don't want to store the result, you can stick it in XZR, because what is the XZR register? It's always 0. Can you write to that? Nope. So if you want to throw away data, that's where you send it. Okay. This would be kind of like, has anybody ever, has anybody used Linux more than what we have this semester? You ever heard of dev null? No? Okay. So on Linux, there's a device where if you send data to it, it just disappears. It's like a black hole of data. And that is called /dev/null. Yeah. And then there's lots of, clever Linux jokes about it. So, okay, anyway. So that's what it's going to do. It's going to subtract one from the other, and then based on that, set the flags appropriately. And then the difference, we don't actually care about the difference, but we do care about the flags that come from it. So that's why it's sending the data, the answer to the 0 register, which doesn't do anything. Okay. And then now the flags have been set to something, and depending on the combination of what the flags are, then that can tell us whether or not we've got greater than, less than, equal, etc. Okay, so let's take, for example, equality. How would we know to branch on equality if we compared 2 registers to each other? Okay, how would this operation tell me equality? Okay, so if I subtract, go ahead.
The 0 flag is set?
Yeah, it'd be if the 0 flag is set because I'm subtracting them, right? So the 2 numbers are the same, means that their difference is precisely 0, which means that the 0 flag would get set to 1. And then a comparison could say, all right, I'm going to look at the 0 flag and branch either yes if it's 1 or don't branch if it's 0. Okay. So that's maybe the simplest one, and that's most like Brookshire, right? Branch on equality. But it's really branching on 0, right? Because internally we're doing this subtraction. So that's why we don't have a flag called E for equality, because we don't really need it. We can recast it in terms of 0. Okay. All right. And so, like I said, there are, oops. Go on to the next slide here. There are 16 different options for your branch instruction, and they're going to use different combinations of the flags. Okay, so I think on here I've got this is the PDF from ARM. Okay, here's the conditions. Oops. Okay, so it doesn't actually list them here anyway. But the encoding for this, by the way, is you've got 4 bits to set the type of branch condition. That gives you 16 different possibilities. Okay, I think maybe it's in here. Branch instructions, that's what I want. Okay, so page 7. No, that's not what I wanted either. Okay. I wanted to show you what all 16 of them were, but I don't seem to have it handy. So let's see what Okay, which file is it I have here? I've got the there's the download button. Come on. There we go. Okay, so let me make sure this is the correct thing I'm looking for. To see, like I said, all 16 combinations, but most importantly, and why I want to show it to you guys, is to look at sort of the different combinations of the flags that we could care about, right? So the equality or not equality are both going to look at the zero flag, and that's it, right? Because if they're not equal, then what happens when you subtract them? Yeah, you don't get zero, and so the zero flag gets set to zero, okay? Oh, that's lovely, thank you. Try again. But some of the different conditions, like how, for example, would we be able to determine less than or equal to? Well, equal to we can determine if the zero flag is set, right? But how would we determine less than if, how would we know if, for example, x1 is less than x0? If we subtract them, x1, or sorry, if we subtract x0 from x1 and x0 is bigger, then what's going to happen to the flags? Huh? The negative flag will get set. So less than or equal, what we would be looking for is either the negative flag set or the zero flag set. Does that make sense? Okay, or like for greater than, maybe it's going to be the other way, is the negative flag not set or the zero flag set, right? So there's all those different kind of Boolean combinations that we could have. Okay, please hopefully be the correct file that I'm looking for. ARM's website doesn't really make it super easy to find all of the references. And what's most annoying is that they change them all the time, and so like you find something and then yes, except it's hundreds of pages. Yeah, okay. So this is yeah, this is the full one. Okay, so all right, so let me open this in a real uh, thingy. Okay, so we want, where did it save this? There it is. Okay. That's not the droid I was looking for. Oh, it's still loading. That's the problem. There it goes. Okay, so what I wanted to do was, yeah, see, look at how many pages that is. 8,000 pages. Okay. Whoa, whoop-de-doo. Okay, yeah, well, it is 50%. All right, let's see if we can find branch with conditional in here anywhere. Okay, so branch on condition page C6816. Okay, that was not what I was looking for. Oh wait, here we go. Okay, you know what? Let's not waste our time with this, but I'll find the cheat sheet where this is not hard to look at, and we don't have to go digging through an 8,000-page manual. Okay. You guys thought Dr. Himsel gave, or Professor Himsel gave evil reading assignments. No. Well, I ran into a couple guys yesterday, and they're like, yeah, so who were in con law with Dr. Himsel right this instant. And at like 4 o'clock yesterday afternoon, he's like, assigned them a 23-page case to brief. Just like, surprise. Yeah. Anyway, law works. Yeah, pretty much. Okay. Anyway, so I'll find the cheat sheet for this. I found it before, but whatever. Okay. So there are two specialized instructions that do sort of a comparison and a branch together in one instruction, but there's sort of only two variants of it. And in a sense, these are basically a comparison and a branch put together in a single instruction, and they are CBZ and CBNZ. Compare branch 0, compare branch non-zero. Okay, that's what they stand for. These do not update the flags, but they're genuinely a single instruction. Okay, so we could get compare branch and 0 by doing compare and then branch equality, but that would be two instructions. Okay, and it would take however long two instructions take to execute. Whereas the compare branch 0 instruction, CBZ, would do that in a single instruction. And it is genuinely different than the other ones because, so if we dig into our little spreadsheet that's got, well, it's not so little, but if we dig into our spreadsheet that's got all the opcodes and stuff, we can see that these two things genuinely have different opcodes. Okay, and so they are genuinely different instructions. Now, why is this maybe useful to have these things as a single instruction rather than having to do a compare and a branch every time? It's faster, right? And what I mean, just kind of think about what's the most common situation that you're going to be branching on. Yeah, well, yeah, but like what condition would be probably the one that you're going to use the most? Equal or non-equal, right? And so hence why these two things are special, right? Less than or equal to, right? Do you really need to do a less than or equal to? Because like, for example, if I wanted to say for int I equals 0, I less than or equal to 4, I plus plus, how else could I do that? I could say int I equals 0, I less than 5, I plus plus, and then check whether or not I'm equal to 5, rather than whether or not I'm less than or equal to 4. Right, so does that kind of make sense? Right, so you could, the inequalities, right, you can recast them if you're clever, and therefore be able to use a faster condition. I mean, we're only talking the difference of one machine cycle, basically, but you know, if you really, really, really want your code to get fast, then this is the kind of witchcraft you have to resort to. Okay, good. All right, so all right, that's it for the PowerPoint. Okay, but there is, so let's just sort of recap. We had unconditional branches of two flavors. Immediate, where you basically are specifying a label, which eventually gets basically to be just a memory address, or unconditional branch to the value that's sitting inside a register, where you know the memory location in advance. Okay. Then the the conditional branches are going to be based off flags, and the most common ones are probably going to be 0 and non-zero, but you do have the others if needed. Okay, so let me let me close this, and I should save that because I put in those commas that were missing. Okay, this thing is, I'll just close that. And I'll find a little cheat sheet for these in terms of which flags they look at and which flags they don't, and post that to Canvas because it's kind of handy. Okay, so let's take, let me just open up Genie and let's just write something. Okay, so let me do a new project. Okay, and let me call this subroutines project. And I'm going to do the following. So I'm going to do okay, I'm going to do some stuff in C, and then we'll assemble it and kind of look at what we get again. Right. So when you guys wrote stuff in Java or C, right? Did the entire chunk of code all go in the main procedure? Of course not. What did you do? Yeah, you had other functions that you wrote, subroutines of some sort. Okay. And those subroutines, like the main function, could have an input or inputs, and they could have an output or outputs, right? So you could, for example, pass two numbers to a routine and then get back a single number, or you could pass a number to a routine and get back something, or you could pass nothing to a routine and it would just do something, okay? And you guys looked at every sort of combination of that kind of idea, right? Okay, so let's write a stupid function or a stupid program. So what I'm going to do is first off, let's just define a number of some sort. Okay, so and just to remind ourselves, what's the difference between a long int and an int? An int, regular int is, yeah. Now I should say that depends on the architecture and which compiler you're using, because if you go back 20 years, long int was 32 bits and int was 16, and then people talked about long ints, which were 64 bits, right? So anyway, but for our purposes, int is 32-bit, long is 64-bit. Okay, so how would I write a subroutine that would say square a given number? Okay, what would the routine be? So first off, what type of data is it going to take in and output? If it's going to take in a number, square it, and spit it out. It's going to take in, well, a long int. Okay, and then I have to specify what's the local variable that I'm going to call what gets passed to it. How about n? That's a perfectly good choice. Okay, and then what am I going to do? I'm going to return, well, n times n, right? Okay, now there's two things here. First off, we're doing multiplication. We've never actually used that instruction yet, but it's going to spit out a multiplication instruction. The ARM architecture does have a hardware multiplier for integers and also for floating point. Okay, when some of you guys, when you were in 101 with me with Brookshire, we did the multiplication project. And what was so joyous about that, there was no hardware multiplier. There was no instruction to do it. So you had to code by hand the entire multiplication algorithm. And wasn't that so exciting? Well, for you guys, and this is why you ended up as CS majors, right? Hmm?
Encode the multiplication. Didn't we just what's it called when you take the bit?
Oh, the
Bit shifted.
yeah. Well, that's how you multiply or divide by 2,
Yeah.
right? So and that was the trick in the Russian peasant method, right? Was bit shifting. But okay, point being, when we did this in Brookshire, or if we were to go back and do this, say, on the 6502 or some of these old processors, they didn't have hardware multipliers. And so if you wanted to multiply, you had to come up with some other rigmarole to do it. Okay. ARM fortunately has this. Okay. Fortunately has a single multiply instruction, and the syntax for it is basically just like a add instruction, except it's multiplying. Okay, that's all. Okay, so we'll give this routine an integer, and it'll spit back out the square of this. Okay, and then let's return, or actually, what do we need to do here? We need to do square of num, and well, how about I do this? Oops. How about I just return the squared number, right? Okay, so the main function is going to pass the number 5 to the subroutine. Subroutine is going to square it and hand it back, and then the main function is going to hand that back to the operating system, and that's it. Okay, not a particularly exciting program. All right, let's compile it and see what happens. Um, oh, yeah. Well, what did I mess up here, guys? Implicit definition, huh? Yeah, all right. Well, let's see. Well, why don't I just maybe it doesn't like the fact that I'm using the word square. So let me just say func. See if it likes that better. Nope, doesn't like that either. Okay, so what do I have to do? I probably have to put this there. Um, okay, there we go. Good. All right, so let's look at the assembly that just got spit out by this thing. Okay, and there's, of course, a lot of this stuff that's going to be kind of garbage that we can ignore, but let's sort of look at what's the important stuff here. Okay. Okay, so where's the main routine? Okay, so we've got two functions, right? We've got the func function, okay, and it's going to do some stuff, right? And notice that what's the sort of important part for the func thing is that line there where it is going to um, sorry, it's going to do the multiplication, right? Okay, so look at where the registers, what registers are listed here. Okay, x0, x1, x0. So the first x0 tells me where the answer is going to be put, right? And then the second two things, x1 and x0, tell me the two numbers that I'm going to multiply. Okay, now in this case, what gets loaded into x1 and x0? Look at the two instructions up above it. The same number, right? Okay, and that makes sense because we're multiplying a number by itself. All right. But why is it that the compiler put these things in x0 and x1 for a function? And in fact, this is going to be the thing that maybe blows y'all's minds, is I actually could delete these 3 instructions right there. Okay, because what's going to happen is when we go into a subroutine, there's a convention as to how do you pass parameters to that subroutine. You put things in registers, and then you go into the subroutine, and the subroutine is expecting things to be in certain registers. Okay, so there's a calling convention here. If you have lots of things to pass, then you have to put it on the stack and then pass memory addresses and stuff like that. We'll talk about the stack later. But for a simple function like this, where you're just passing a single number, it should expect that number to be an x0. And if you're passing 2 numbers, where should they be? x0 and x1. Okay, and so on. But then also, the convention is when you pass an answer back from a subroutine, if you're going to pass a single number back, where should it be located right before you return? x0. And if you're passing 3 things back, it'd be x0, x1, and x2, okay? And kind of so on. If you're passing back like a million things, then you're going to be storing stuff to memory and not doing it with registers. But if it's just a single number or something, then a register is all you need. Okay. So notice that whatever happens with the multiplication, the answer is in x0, and then I return from this subroutine back to who called it, which was the main routine. Okay, good? Yeah? All right, so let's look at the main routine. Okay, this line right here is the important one. Okay, so what's happening up above? Okay, so there's some offset stuff and some stack pointer, blah, and whatever. Okay, we load the number 5 that I chose in advance here, okay, into the register. Okay, great. It's storing that in memory. It's loading it back out of memory just to be inefficient. But that's the magic instruction that is important for our purposes. BL. What does the L stand for? Is the question, right? And I don't expect you guys to know this. The L stands for link. So what's going to happen for me to pass to a subroutine and then be able to return from the subroutine? Okay, so this is something that's a little bit hidden when we're looking at assembly, but Brookshire made much more clear. How does a computer, how does a processor execute a program? What is a program, really? Well, yeah, okay, a little higher level than that, sorry. And when I say high level, I mean like not that ones and zeros is an insult, but just, you know, an abstraction level above that. It's a sequence of instructions that are encoded in binary according to some scheme, and they're sitting in memory in consecutive memory cells. Okay, so how does a processor execute them? Well, there's a program counter. Okay, and what does the program counter start as? What's the very first value of it? Well, it depends on the architecture. In Brookshire, what was it always? 0, 0, right? In the ARM architecture, it's not necessarily 0, but it's going to be wherever the beginning memory cell that has your program in it, right? So your program is going to be sitting someplace in memory, and let's say it starts at memory cell 1 billion, then the program counter would be 1 billion, and you would say, oh, okay, I'm pointing to this memory cell. That's where my first instruction is going to be. So I'm going to load that instruction in. I'm going to figure out what it says to do. I'm going to do it. And then what? Then what does the program counter become? It will point to the next instruction, okay, which on ARM is going to be what? If I started on 1 billion, then the next one would be Eat 1,000,000,004. Okay, why 1,000,000,004? Because every instruction on this architecture takes how many bytes? Quatre byte, quatre octet. Okay, on Brookshire, what was it? It would increment by 2 because each instruction took 16 bits. Okay, and this is the annoying part of, say, the 6502 architecture. Not all the instructions there were the same length, so you would have to know what kind of instruction you had to then determine whether or not you added 1 or 2 or 4 or whatever to your program counter. Okay, so the program counter is pointing to a place in memory. Okay, but there's only one program counter, right? Okay, so if I pass to a subroutine, that subroutine is sitting someplace else in memory. Okay, which means for me to go there, I have to change the program counter to be the new memory address of wherever the new routine is. Okay, so let's think about this in Brookshire. You guys have done this, right? That if I want to jump to someplace else in the program or a subroutine, I have to say, what's the memory address I'm jumping to? Makes sense, right? If you jump to something in Brookshire, is there any record of where you came from? Nope, which means there's no way to return back. Okay, so what this means is that in Brookshire, there's no automatic way, you can hack it if you're clever, to return from whence you came. Okay, does that distinction kind of make sense here? Right? So let's say I'm currently executing the instruction at memory address 10, and it tells me jump to memory address 80. So I say, okay, I jump to memory address 80, I start doing anything. On Brookshire, there is no record that I jumped to 80 from 10. So the previous value of the program counter before the jump was not saved anywhere. Okay, and in fact, there's no way to save it because there's no instruction that gives you access to the program counter on Brookshire. So guess what Dr. McKinney would change for Brookshire 2.0? That. Okay, I'd make it so that you could read the contents of the program counter. Okay, Evan. In ARM, yes. Okay, and in pretty much every architecture under the sun, yes. Ah, okay. Well, how does it help you as programmers? Well, let me go back to the C. Okay, if I'm going to execute, oh, it would help if I used a correct mouse for this. If I'm going to execute this function, the main function is going to call the func function, okay? But then after the func function runs, it comes back to the main function. Well, how does it know how to get back there? Or where to go back in the main function? This record of where you came from. Will, you had a question? Okay. So, because for example, let's say that I had some other stuff here like, oh, I don't know, I'm just gonna, just put in something useless, okay? But the I need to record not just that I was coming from the main function, but where within it I was coming from. Okay, because otherwise I might go back and try and start the whole thing over again and get myself into an endless loop. This, by the way, is how recursion works, okay, on an actual machine, is we're going to set the program counter to a new value, but record what its old value was before we did it so that we can go back to that old value. Okay, does that make sense? All right, so let me just delete this stupid line because it didn't actually do anything. Okay, so going back to the main thing, so right here, okay, the branch and link. So what's going to happen when we branch and link to a function, okay, is that branch and link is always going to have another instruction that it's paired with, and that's this dude down here, return. Okay, so what branch and link is going to do? Well, and notice that up in the func function, the one that squared it, there was a return. Okay, so the instruction branch and link is going to say, okay, I'm going to set my program counter's value to the memory address where the function func starts. And right before I do that, I'm going to write down what my current program counter value is so that I know where to go back to. Okay, does that kind of make sense? No? Yes? You guys seem mystified.
So it sets it when you're in main.
And then, right?
Okay.
And then when you hit the return command in func, it's going to say, okay, I jumped to this instruction from, let's say, memory address 27. Or, well, okay, let me use powers of 2. Okay, so let's say the program counter is 32, and I hit the BL instruction. So I'm going to say, all right, I'm going to scribble down on scratch paper that my program counter's value is 32. And I'm going to jump to the func instruction wherever it is. Okay, so I jump to the func instruction. That changed the program counter to, let's say, 64. Let's say that it's down there someplace. Okay, so now my program counter is 64. Load in an instruction, do it. Load in the next instruction, do it. Load in and do stuff. Then I hit the return instruction. And that's going to say, okay, what was the last program counter value? What was squirreled away on my scratch paper? It was the number 32, to which I'm going to add 4 because the next instruction would be at one memory address past that, right? 36, okay? And so now or 32 to 36. Yeah, it started with 32, and so I add 4 to that, and I get 36, yeah? Okay. I mean, I know it's 9 o'clock, but I mean, I've had at least a third of my coffee, okay? Okay, so point being, I'm going to go back to my scratch paper and say, all right, what was the program counter before I entered this subroutine? And so that I can go back to the instruction. So if this was cell 32, the next instruction after that would be in cell 36. So I'm going to say, all right, program counter, now you're 36. Bam, that takes you right back to the line immediately after the BL instruction. And then I continue on and do the rest of the stuff. Okay. Okay, so this maybe is a little bit easier to see. Because I wrote this in C, I can't do the GNU debugger the way that I want to. Okay, but I do have a different, where did I do? Okay, I had this one, okay, my chocolate routine. So let me just load, well, actually, I'll load it in Genie here so that it's easier to see. Okay, this guy here, where I'm going to, this is much more readable because it was handwritten assembly. I didn't start with C and compile it. So what do? I've got a main function that's going to take in 2 numbers and it's going to pass them to this chocolate routine. And it's going to do that a couple of different times. Okay. So let's go through here and run this in GDB and watch what's happening with the registers. Okay. Are we cool? Yeah? Okay. So let's go into, I wanted to do, Okay, so all right, let me blow this up so that it's as big as possible. Okay, so when I do the info registers, right, it's going to be spitting out a whole bunch of stuff. A lot of this is garbage that we can ignore because what real registers do we care about right now? Probably just 0 and then maybe 0 and 1 at some point. Okay, but there's all sorts of gobbledygook various in various places. Okay, and then here's where I really want to concentrate for right this instant, which is this line here. Okay, so what is that line? What is that telling me? Which register am I looking at? I'm looking at the program counter. Okay, so the OS loaded this thing into memory at memory cell 55555555774. Okay, and it's 778 because it's where main started plus 4 bytes. Okay, because I just went through one instruction already. Okay, so that number is going to increment obviously by 4s. Okay, so if I step, the next instruction is this. Okay, and if I do info registers, okay, what's the program counter now? Main plus 8. Okay, so it's 55557C. Okay, great. And then let's continue. Okay, I don't care about that one. I don't care about this one. I do care about that one. Okay, so where am I right now? I'm about to execute the branch instruction. Okay, where am I? I'm at currently at memory address blah, right? So bunch of 5s, 788. It just happens to be where it is. Okay, good. All right, so I'm going to step, and now I'm inside the chocolate routine. So I just got passed to him, or actually I'm about to. Okay, now look at what the where am I? Where's my program counter? It's inside the first instruction of chocolate, which starts in memory cell 7C0. What was the previous value that we had there? It was what, 778? Okay, which is a bit backwards in memory, right? So we've just jumped to a new memory location. Okay, and so the 778 address, that got stored someplace. Okay, it got stored on the stack. And so when I finish the chocolate routine, where am I going to go back to? Okay, so if I step, okay, so what did the chocolate routine do? Let's just go over to Genie real quick. The chocolate routine just squared the number. That was it. Okay, so nothing exotic. So it was really only 2 instructions. Okay. All right, and so I'm about to hit the ret. Okay. What's my program counter? Well, I'm now on the second instruction in chocolate, right? So I'm 4 bytes down from where I started. Okay, great. What's going to happen if I step one more time? Now I'm going back to the main instruction, but how did I know where to go? Because I had previously recorded the program counter's value. And where am I now? Main plus 24. Okay, meaning, 7, 8, blah, 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 blah. Okay, does this kind of make sense? You could not do this in Brookshire in an automated way. And I say automated to mean that, well, is there a return instruction on Brookshire? No, nor is there a branch and link or jump and link or anything like that, right? So you could do a subroutine, but you had to know in advance by writing this on paper or something what the memory address to go back to was, and then hard code to jump back to it. Okay, yeah, Will. You mean the old value? It gets stored onto the stack, which we'll talk more about stacks and how those work later. Um, yeah. So this is actually an interesting point. So our stack here is kind of serves two roles. It will get used as sort of temporary memory storage spots, and that includes previous values of program counters or just data. Okay, which means we'll have to kind of keep straight what's what. Now, different architectures handled this differently. So, for example, the 6502 architecture. Let me actually load something because I think this is actually somewhat illuminating. Okay, and then let me load a Nintendo architecture. Okay, and then I'm going to load an assembly one. So the way this architecture worked is it could address, and this will take a minute to load, probably there it goes. It could address 64 kilobytes worth of memory, okay? And the way that it was done is it was divided into 256 pages. So you could imagine the memory as being like a book that had 256 pages in it. And each page had 256 bytes on it. 256 squared is 64K. Okay. So on each page, you can imagine that there was a 16 by 16 grid, just like the memory on Brookshire. Okay. But you had 256 pages worth of those instead of just one like you did with Brookshire. So what it did was page one was a special page. That's where the stack went. Okay, but on that architecture, you only used that page for the call stack, meaning old values of program counters would get stored there. Okay, and then if you wanted to have a stack of just other data, you would have to keep track of it someplace else. Um, and so, like if we go into, we want the VRAM browser, or here we go, memory browser, right? So it would be divided into pages. And here, the call stack, well, there's no call stack on this because this program just prints hello world and that's it, right? So nothing special happens. But if we had a more exotic program, so like let me load in one of the more exotic ones here that actually does stuff. Okay. Then there's a stack of previous subroutine calls. Okay. And that stuff's getting stored someplace because it's not as if like the processor's psychic and remembers where like that data has to be someplace. Okay. Um, and that thing is the stack, which we'll talk about a lot more later. Okay. Okay. So branching and linking is how you get subroutines, but it's also because if that's how you get subroutines, that's also how you get recursion. Right. So what is recursion? Okay. So in our example here, I had a main function that called the chocolate function or the func function, whatever, right? What makes something recursive?
Calling itself.
If chocolate would call itself or main would call itself or something like that, okay? There's nothing that says you can't do that, but how it's happening is you're just recording the program counter and hopefully the other numbers and stuff so that you don't end up in an infinite recursion, because that's usually bad. Okay. All right. You guys are all, oh, there's Noah. He just woke up. Death. So you guys all start chomping at the bit at 9:10 or 9:05. When does class end? 9:15. That means you have to deal with my annoying voice for 4 more minutes, or 3.5 more minutes, or what? You could. The door's right there. Don't let it hit your ass on the way out. Okay. So, right. So let's go back to the chocolate thing for a second. Okay. And look at, so this return or the branch and link instruction, right, are going to be storing information to the stack, namely the program counter's value. Okay, because that info's got to be stored someplace. And then if it's stored someplace, we can access it when we hit a return instruction. Okay. So I guess what would be good, maybe I'll let you guys do this for next time, is we had our little handy dandy spreadsheet, right, of the different opcodes and stuff, and then the little reference sheet. Go find the return and the branch and link instructions in the reference and the reference spreadsheet, and just see what's there. Okay, this is called RTFM. Read the manual. Okay. All right. Well, we'll go ahead and quit, and I will see you guys. Jack, no, I haven't put the PowerPoint in Canvas. I forgot to. I'll do that. Anyway, so all right. See you guys later.